Hi, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we drift to Proxima Centauri b, a small rocky world orbiting the red dwarf next door. We'll quietly consider how Earth-like it might be, whether it could host life, and what it might take to go there. Dim the lights, get comfortable, and let's begin. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and thank you so much for being here. Proxima Centauri sits a little over 4 light-years away, close by cosmic standards, unimaginably far by human ones. It's a red dwarf, smaller and cooler than the Sun, glowing a deep, steady red punctuated by sudden flares. In 2016, tiny regular wobbles in Proxima's motion betrayed the presence of a planet tugging on it, Proxima Centauri b. Those wobbles, the radial velocity method, let astronomers measure the planet's minimum mass, roughly comparable to Earth's, and its short year of about 11 days. Because the star is faint, the planet orbits very close in by our standards, at a fraction of Mercury's distance, yet it receives roughly a sun-like fraction of starlight, on the order of 2/3 to 3/4 of Earth's, putting it in the star's habitable zone by the simplest definition, far enough to avoid a permanent oven, close enough to avoid a permanent snowball. The discovery mattered not just because it was nearby, but because it said something bold. The galaxy may be full of small, rocky worlds in clement-looking orbits, even around tiny red stars that vastly outnumber sun-like stars. But we must be careful with words. Habitable zone does not mean habitable. It means possible, given enough of the right conditions. And proximity does not mean reachable in any practical sense today. It means first on the list for the next generations of telescopes and one day probes. Proxima b does not routinely cross its star from our line of sight. No reliable transits have been confirmed, so we cannot, for now, read its atmospheric fingerprints by backlighting the planet with the star. Instead, we learn indirectly, from the star's temperament, from the planet's gravity inferred via its pull on the star, from climate and escape models, and from the hardware we're building to tease out faint planetary light right next to a flickering red sun. Even at this sketchy stage, 3 truths shape every scene you will imagine. 1. The planet probably presents the same face to its star most of the time. Tidal effects are strong in close orbits. 2. The star's high-energy radiation and flares are harsher than Earth receives. And 3. Heat and air, if they exist, must circulate efficiently to keep water liquid somewhere. Keep those in your pocket as we walk forward, because Proxima b's story is a tug of war between hope, a small rocky world lit gently over all, and hazard, a nervous red sun that can strip, scorch and stir. Proxima Centauri is a tiny furnace running slow, cooler than the Sun, with a surface temperature closer to an electric stove coil than to our star's white blaze. It sips fuel. It will live for trillions of years while sun-like stars die, but it also bursts with magnetic tantrums. Red dwarfs churn and tangle their internal magnetic fields. When those lines snap, they hurl flares that spike in ultraviolet and X-rays and drive swollen gusts of stellar wind. For a world tucked in close to stay warm, those outbursts are not weather. They are geology-level forces. High-energy photons can break apart water and carbon dioxide, driving chemical chains that thin ozone and change how lower layers of air handle heat. Winds and coronal mass ejections can ram into upper atmospheres, heat them and peel them away, unless gravity, cooling, and a magnetic field fight back. Yet a red dwarf's cool, steady output between flares means the average visible infrared warmth can feel gentle. If Proxima b holds onto air and water, the star's spectrum shifts the way light paints the ground and sky. Daylight would be deeper red compared to Earth. Shadows may look softer and warmer, and plant-like life, if it evolved, might favor different pigments to harvest in the near-infrared where the star is richest. Another rule from the star: the pre-main sequence youth of red dwarfs is brighter than their adult phase. For hundreds of millions of years early on, Proxima would have been far more intense relative to its adult output. A young Proxima b could have faced a steam bath greenhouse, losing oceans to space if it started with Earth-like water and a thin air. On the other hand, if it began with abundant water, for example delivered by icy bodies, or built a thick atmosphere via volcanism and retained a magnetic field, it might have endured, ending up with a robust blanket today. The star's spectrum also changes photochemistry. The familiar ozone layer on Earth forms under UV. Different UV ratios could build thinner or patchier ozone, changing how deeply harmful light penetrates. That matters for surface biology, but less for subsurface or underwater life, which might find safe niches even under a lively sky. In every climate run you'll read about Proxima b, designers must feed in the same stellar character: calm red warmth, frequent high-energy slap, slow aging. The planet's answers: keep a thick coat, circulate heat, replenish volatiles, must be steady for billions of years, or habitability becomes a punctuated thing, on and off between eras of erosion and repair. The good news is that red dwarfs give you time. If a world makes it to stability, its star won't die on it. The hard news is surviving the youth and the moods. From the star's wobble, we get a period of roughly 11 days and a semi-major axis only a few % of Earth's orbital radius. Call it approximately 0.05 astronomical units, give or take refinements. We also get a minimum mass in the neighborhood of Earth's, around 1.2 to 1.4 Earth masses, because the radial velocity trick sees only the component of motion along our line of sight. Unless we know the orbital tilt precisely, we say at least this heavy. Put those together and you get a first pass at surface gravity, likely comparable to or a bit higher than Earth's, which helps an atmosphere stay put. Now pour in the star's luminosity. Proxima radiates well under 1% of the Sun's total power, so a planet must sit close to get enough. Do the simple flux math, and you find Proxima b receives a healthy fraction of Earth's sunlight, often quoted around 0.6 to 0.7 times our insolation. If the planet had Earth-like reflectivity and no greenhouse blanket, its bare equilibrium temperature would come out cold, colder than Earth's, but greenhouse gases and circulation change everything. The expected tidal timescale at such distances is short. The planet is likely synchronous, keeping one face toward the star, or perhaps in a spin-orbit resonance that still produces a near-permanent day-night contrast. That contrast is the whole game. Picture a day side that never sets, steady red sun overhead, a night side that never sees sunrise, a deep, starlit, cold trap. If there's an atmosphere thick enough, winds and waves transport heat, smoothing extremes. If the air is too thin, the night side can become a cold sink that freezes out gases, robbing the day of breath and collapsing circulation. GCMS, global climate models adapted from Earth's playbook, show that even a few tenths of a bar of CO2-rich air can keep a dark hemisphere from freezing solid. Add water vapor, clouds, and perhaps a shallow ocean, and the system starts to look surprisingly resilient. The star's lower visible blue output means less energy drives. Rayleigh scattering. Skies on the day side might look more copper or salmon than blue, depending on aerosols and haze. Clouds cluster where rising air cools. The substellar point could carry a permanent bright cloud shield, reflecting light and moderating surface temperatures below. Around the terminator, the ring dividing day and night, temperatures may hover in a narrow band that many models flag as clement even when dayside bakes and nightside chills. This terminator habitability shows up again and again. A world can be both extreme and welcoming if circulation hums. Finally, the lack of confirmed transits means the orbital tilt likely misses our line of sight. That's a measurement nuisance, not a climate crisis. It keeps us from reading starlight through the air directly for now, but it doesn't change the basic heat budget or the grip of tides. Whether Proxima b is friendly depends on whether it kept an atmosphere and surface water. High-energy photons can split water into hydrogen and oxygen. Hydrogen, light and speedy, can escape. Oxygen can rust rocks or accumulate if not balanced by outgassing and life. Stellar wind and flares strip at the top while gravity and cooling pull back. A magnetic field helps by deflecting charged particles, but it is not a force field. Energy still couples into the upper atmosphere through polar caps and currents. Does Proxima b have a dynamo? That hinges on interior heat, from formation and radioactivity, rotation, which tides may slow, and core composition. Synchronous rotation does not forbid a dynamo. What matters is internal convection and at least some spin. Even without a big magnetosphere, a dense atmosphere can bear the brunt. Venus is the poster child. No strong global field, but a thick CO2 cloak that the sun has not blown away. Early epochs may have been harshest. Young red dwarfs stay luminous longer than sun-like stars for a given mass. Proxima b could have endured a runaway greenhouse until the star dimmed, risking ocean loss. Yet initial conditions are a wild card. If the planet formed farther out and migrated inward, it may have carried deep water reserves. If it began with more mass than Earth, its stronger gravity could lock gases better. Volcanism can refill what space takes, and an ocean rock carbon cycle can buffer CO2 if liquid water is present. Upper air chemistry under an M-dwarf spectrum also differs. UV splits and recombines in patterns that can make abiotic O2 or CO pockets that mimic or mask biosignatures. Even haze formation, those photochemical smogs that cool by reflecting, depends on short-wave photons that Proxima supplies differently from the Sun. Models produce three broad families of outcomes. In the stripped family, the planet wears a thin coat or none. Surface is dry or ice-armored, temperature swings are brutal, and habitability, if any, lives underground. In the robust air family, a bar or more of CO2/N2/H2O shields the surface, circulates heat, and keeps the night side from collapse. In the ocean world family, a deep global sea with modest atmosphere handles transport, while the surface lacks continents, changing carbon cycling and nutrient flows. Between these cite mixed cases: patchy seas, high plateaus under clear skies, caldera-fed oases lit by a ruddy, unwavering sun. None of these violate physics. The planet's path from birth through stellar tantrums decides. Because we cannot peak directly yet, the wise posture is agnostic optimism. Assume nature tries all knobs and plan instruments that can distinguish thick from thin airs, wet from dry surfaces, oxidized from reduced chemistries, and circulation patterns that betray a living, breathing climate. Imagine ground truth in broad strokes. On a synchronous Proxima b with air and water, the day side points at a red sun fixed in the sky, climbing only a little with seasons if the tilt is mild. Near the substellar point, warm surface and rising moist air grow a thick, bright cloud shield that reflects a chunk of incoming light, keeping temperatures below what you'd fear. Think of a permanent late-morning glare behind high milky anvils. Move outward, and the cloud deck thins to patches. Winds, driven by the giant day-night temperature contrast, blow from day to night aloft and from night to day near the surface, closing loops that never sleep. Along the terminator, the thin twilight girdle, conditions can settle into the most Earth-like mix: mild temperatures, soft perpetual sunset lighting, and steady breezes. It is here that many climate studies find persistent liquid water even when the night side hosts ice and the day side runs warm. Sail a notional ocean there, and you might see pancake ice drifting from the dark, fog ribboning above cool swells, and a copper light that never brightens or fades much. Dive under, and the world grows safer quickly. Water filters UV and smothers flares to harmless flickers of brightness. If the planet lacks a lot of water, the day side might host desert basins beneath broken clouds, while the night side grows glaciers that flow slowly toward twilight, carving into a ring of melt where temperatures allow. The sky hue depends on air molecules and aerosols. With less blue scattering from a red star, the dome could skew to tan or salmon, with white clouds tinged peach. Plants, if nature found them, might not be green. Under an M-dwarf, photosynthesis could soak in the near-infrared. Pigments might look deep red, brown, or even near black to gobble sparse photons, though reflectance could still carve strange red edges that telescopes one day could seek. Night is a world apart. Stars crawl in slow arcs if you walk east or west along the terminator. On the deep night side, air thins and chills, and any settlement would burrow or bring heat. Lightning? Likely, convection under the substellar cloud has the ingredients. Thunder never meets sunrise, only a dim, permanent dusk at the horizon. Rivers, if continents exist, would tend to flow from night to day, melting at the twilight band and evaporating on the hot side, feeding an endless hydrologic treadmill that does not track days but positions. This eyeball Earth pattern, dark ice pupil, bright cloudy iris, clearer rim, appears again and again in models with a little water. It's alien, but not hostile by definition. The deciding factors remain air mass, water inventory, and stellar mood. If those are favourable, the ring of sunset could be home to mild seas forever, lit by a star that barely moves. Words like Earth-like tempt shortcuts. Mass near Earth's? Rocky, probably. In the habitable zone by flux? Temperatures could allow liquid water somewhere if air and water exist. But Earth-like in daily feel is another matter. Earth spins fast. Proxima b likely does not. Earth's sky is blue with a yellow sun that rises and sets. Proxima b's day may be fixed, its sky copper, its bright clouds bunched in one hemisphere. Earth's star is comparatively quiet. Proxima's is volatile on short timescales and was bright in youth for a long time. Earth's ozone, magnetosphere, and thick air collaborate to keep the ground benign. Proxima b must assemble an equivalent shield from a different starting kit. The habitable zone is a geometric idea about distance and starlight, not a promise. To turn possible into plausible, 3 boxes must be ticked for billions of years. 1. Volatiles, water, CO2, N2 or other background gas, must be present in the right amounts. 2. Retention must win against erosion. Gravity, cooling, magnetic deflection, replenishment from inside. And 3. Circulation must distribute heat so that water neither all freezes nor all boils away. Habitability can be patchy in space. Terminator rings, dayside oases, subsurface seas, and episodic in time, eras of loss and resupply. And there are false friends. A planet with abundant oxygen is not automatically alive. UV-driven water loss can stockpile O2 abiotically. High methane plus oxygen smells like biology on Earth, but exotic mantle chemistry could confuse interpreters. Even the Earth Similarity Index you may see online is a simple mash of radius, density, temperature proxies. It is a rough flag, not a diagnosis. What we can say responsibly is this: Proxima b is a high-value target. It is massive enough to be rocky, close enough to be studied, and positioned where climate physics does not rule out liquid water. Around such a star, worlds can be long-lived. The core threats, early runaway greenhouse and prolonged XUV and wind, are serious but not fatal in all histories. The payoff for patience is large. If we find a robust atmosphere with signs of circulation, for example, heat redistributed between day and night, inferred from thermal phase signals in future instruments, we will learn not just about a neighbour, but about a whole class of planets that likely outnumber sun-warmed twins. If we find a bare rock, we also learn about red-dwarf temperaments, about thresholds for escape, and about how to rank targets around quieter stars next time. Either way, Proxima b is valuable. It is our nearest controlled experiment on what habitable really means when the light is red, the year is 11 days, and the sun gets angry before lunch. Start with the simple picture. A close-in world around a flaring red dwarf is bathed in far more high-energy radiation, extreme ultraviolet and soft X-rays, than Earth receives from our sun on quiet days. Those short wavelength photons heat the very top of an atmosphere, puffing it up. Once gas is expanded and hot, the lightest pieces, hydrogen first, can reach escape speeds and leak away. Add the star's charged particle wind and occasional coronal mass ejections, and you have a constant sandblaster at the planet's edge. That is the loss side of the ledger. The keep side has several entries. Gravity matters. A slightly heavier than Earth world pulls harder on gas. Cooling matters. Molecules that radiate heat away in the upper atmosphere, like CO2 at specific infrared bands, can lower temperatures and shrink the puffed layer, reducing escape. Magnetism helps, not by erecting a sci-fi force field, but by diverting much of the charged wind around the planet. Less of that wind slams directly into upper air and sputters it away. A dynamo large enough to do the job requires a convecting, electrically conducting core and some rotational energy. Tidal locking slows surface spin, but it does not forbid interior motion. Meanwhile, the planet can replenish what it loses. Volcanism vents CO2, H2O, SO2, and other gases from the mantle. If there is an ocean and weathering, the carbonate-silicate cycle trades CO2 between air, water, and rock to buffer climate over long spans. Impacts, if the system holds debris, can deliver volatiles, though big ones can also strip. Early time is the danger zone. Young M-dwarfs shine more fiercely than their adult selves for a long childhood. Proxima b, in its first few 100 million years, might have simmered under a greenhouse sky with water vapor high in the atmosphere where UV easily splits it. Hydrogen would have fled first, leaving oxygen behind that could rust the surface or accumulate as a misleading, abiotic O2 atmosphere if sinks were weak. After youth, the star calms in average brightness but keeps magnetic moods. Intense flares still arrive. Survival, then, is not a single test, but a balance sheet over billions of years. Losses from heating, sputtering, ion pickup and flare storms versus gains from degassing, late delivery, and cold side condensation that may trap gases and recycle them. Modelling efforts sweep across parameters and find wide outcomes that are each reasonable. 1. A bare world with only a whisper of gas. 2. A thin air rock that keeps a few tenths of a bar of CO 2/N2 plus water vapor and moves heat well enough for a twilight sea. 3. A robust secondary atmosphere, think 1 to 2 bars or more, sustained by volcanism and protected by cooling in the upper air and maybe a dynamo. And 4. A water-rich world where deep oceans and a modest sky co-manage climate. None of these violate physics. The difference is initial inventory and how the first 500 million years went. If Proxima B's interior stayed hot, if plate-like recycling or plume volcanism resurfaced and vented steadily, if CO2 could radiate the thermosphere cool, and if even a modest magnetosphere hovered, then a long-lived atmosphere is plausible despite the star's temper. If instead the planet started dry, vented little, and faced a harsh extended steam loss phase, it may sit today as a chill rock with chemistry written right on stone. Because we cannot yet look through its sky, the honest stance is to treat both futures seriously and design observations that can tell a breathing world from a silent rock. Think in archetypes. Bare rock. First, no meaningful air, maybe a trace of CO or O2 from surface chemistry, great day-night swings, frost on the night side, and a sun that bakes and cools with no clouds in between. Spectrally, such a world would reflect weakly, radiate strongly on the day side, and show a very steep contrast between day and night in thermal emission. Second, a thin air rock, a few tenths of a bar of mostly CO2 and N2 with water vapor around the substellar region. Here, circulation can keep the night side from vacuum freezing. Clouds gather over the substellar point, brightening the day side and cooling the ground, while the terminator ring holds patches of open water and low clouds. This case is a favorite of climate modelers because it naturally creates the eyeball pattern, an icy or cloud-capped pupil on the day, a dark iris of ocean/land ringed by perpetual dusk. Third, a Venus-like cloak, thick CO2, many bars, sulfur species, and high, bright clouds that reflect much of the star's light. Surface pressure and temperature soar. Habitability as we know it shifts underground. Can a small world around an M-dwarf end there? Yes, if water was lost early and volcanism piled CO2 without a working rock-weathering thermostat. No rain, no rivers, no carbonates. Fourth, an ocean world, abundant water to hundreds of kilometers depth with a modest atmosphere above. Without continents, the classic carbonate-silicate cycle weakens. Climate can still stabilize via clouds and ocean heat transport, but nutrient cycles, and thus surface life if any, look different. High pressure at depth forms exotic ices that cap the mantle. Heat still leaks, but seafloor volcanism behaves differently under weight. Then an edge case, a world that kept a light H2-rich envelope. Even a few % hydrogen can be a powerful greenhouse at these pressures and wavelengths, extending habitability outward. But close in, hydrogen is the easiest to lose. For Proxima B's mass and irradiation, a long-held H2 envelope is unlikely unless replenished, yet not impossible if starting conditions were extreme. Each end state changes the look. Bare and thin air rocks show strong phase curves, big differences as they rotate around the star. Thick air and cloud worlds flatten those curves by redistributing heat and reflecting more. Spectral fingerprints differ. CO2 bands, H O features. If water is present, maybe O4 dimer absorption if oxygen is dense, which can betray abiotic oxygen. Clouds matter twice, once for climate, once for observation, because they mask and mute gases below. And every state can be patchy. Continents mean deserts and lake districts. Mountain ranges mean rain shadows. A frozen night side may send katabatic winds that carve unique cloud arcs at the terminator. When people say Earth-like, they often mean blue oceans, white clouds, brown-green continents, and a day that starts and ends. Proxima B's family of plausible looks includes that vibe only in a narrow slice of parameter space. The wider probability space is stranger. A ring of eternal evening with mild seas, a glare-capped day above bright anvils, and a night that creaks with ice. General circulation models, GCMS, built for Earth can be retrained to a tidally influenced world by changing the day length, the stellar spectrum, and the inflow pattern, permanent day versus permanent night. A robust finding across teams is the formation of a substellar cloud deck. Rising air cools and condenses under the fixed sun, piling thick, bright clouds that reflect enough light to cool the surface below. This feedback widens the inner edge of the habitable zone for slow rotators. You can sit closer to the star and still avoid a runaway greenhouse because the cloud parasol follows the hot spot. Around the limb, winds haul heat from day to night. The stratosphere can be almost isothermal compared to Earth because the heating pattern is fixed, and the jet structures organize differently without a diurnal cycle. Add an ocean, slab or dynamic, and that ocean stores day heat and leaks it into night, flattening temperature contrasts. In thin air runs, say 0.3 to 0.5 bar CO 2 plus N2 with water, nightside temperatures stay well above their airless counterparts. In thick air runs, the whole planet's equator to pole gradient can be small, with extremes appearing mainly as day-night, not north-south. Cloud microphysics alters outcomes. Small shifts in droplet size and condensation nuclei change albedo. Under an M-dwarf's redder light, Rayleigh scattering weakens, so clear skies absorb more. Clouds, however, remain effective reflectors. If the substellar point sits over ocean, deep convection pumps water to cloud tops and keeps the shield bright. Over land, lower humidity can thin clouds, warming the ground. Tides can also heat the interior a little, especially in non-zero eccentricity, boosting volcanism and outgassing, which changes greenhouse gas inventories over geologic time. GCMs flag robust terminator habitability. Even with hot daysides and cold nightsides, a ring exists where surface temperatures hover near freezing to mild, rain cycles form, and winds blow steadily. Not hurricanes, but the kind of perpetual trades a sailor could learn. This ring widens with thicker air and narrows with thinner. Introduce ice albedo feedback. Nightside ice reflects little starlight, there isn't any, but it radiates to space. If ice creeps too far toward the substellar region, it can cool air and invite more ice in a slow march. Conversely, if open water expands toward the day, more vapor feeds clouds that brighten and self-stabilize. Models also explore photochemistry. Under Proxima's UV, ozone layers are often thinner and patchier than Earth's, changing how deep harmful photons reach. Yet even thin ozone plus clouds can protect surface life at many wavelengths. The ocean protects even more. The point of these codes is not to paint one picture, but to find regimes, self-consistent patterns that appear regardless of small details. The big ones for Proxima B are: substellar clouds are allies, twilight can be kind, Oceans, if present, are heat flywheels, and even modest atmospheres can keep the night from stealing the day's breath. On Earth, life and air co-author the spectrum. O2 from photosynthesis rises and stays only because it's constantly renewed. In sunlight, it forms O3, ozone, which leaves a telltale ultraviolet bite and a mid-infrared band. CH4, methane, from biology and geology, coexist with oxygen only because flows are strong. That trio, O2 plus O3 with a dash of CH4, looks promising. But around an M-dwarf, context is everything. Ultraviolet ratios differ, so ozone chemistry shifts. Water loss in youth can stockpile abiotic oxygen. CO from deep photochemistry can linger. Nitrous oxide and sulfur species may ebb and flow under different UV drives. A strong O2 detection without methane could still be a false friend if paired with signs of past steam loss. For example, a very dry stratosphere. And O4 dimer features that scale with high oxygen pressure. Conversely, CH4 in a modest oxidized atmosphere looks more compelling because methane photolyzes readily under UV. To persist, it must be refilled. Even H2 at low levels can be biological or volcanic. At high levels, it implies outgassing or primordial capture. Haze, tholins from photochemistry, flattens spectra and cools climate. It can arise abiotically and hide signatures below. Surface clues matter. A red edge jump in reflectance from plant-like pigments might shift in wavelength under a redder sun if photosynthesizers evolve to sip near infrared. Telescopes one day might see phase-dependent color changes as continents and vegetated belts rotate into view. But none of this is credible without atmosphere first. Is there pressure broadening in lines that implies a bar-level sky? Do thermal phase curves suggest heat redistribution? Is there CO2, almost always a climate actor, H2O, at least in vapor, and a background gas like N2 or CO2 thick enough to move heat? We also need the star's spectrum measured well, from far ultraviolet through near infrared, because that light drives chemistry. Without that, even honest detections can mislead. Biosignatures are rarely one molecule. They are patterns that violate easy non-living explanations given the star, the planet's mass and temperature, and any history we can infer, e.g., evidence for ocean loss versus retention. Anti-biosignatures exist too. Heavy CO in the presence of lots of O2 is hard to keep if biology is active because life tends to scrub CO. A bone-dry air with strong O2 and no water hints at past desiccation, not gardens. The safest path is to stack independent lines, measure gases, measure day-night contrast, seek clouds, estimate pressure, and only then weigh life versus geology. For Proxima b, we're still at the stage of asking, sky or no sky, wet or dry, thick or thin. If future instruments find even a modest variable H2O signature and a climate that moves heat, the conversation about life will move from could be to worth careful, humble testing. Planetary systems love company. Around Proxima, hints of other worlds have emerged from radial velocity campaigns with ever sharper instruments. A very close-in, low-mass inner candidate, often labelled Proxima d in the literature, has been reported with a period of a few days and a fraction of Earth's mass. Such a world would be too hot for surface water, but important dynamically. Claims of a more distant multi-year companion, sometimes dubbed Proxima c, have also surfaced, though interpretations vary and are still debated. If a real outer world exists, it could stir small bodies and seed impacts inward over long timescales, sometimes a hazard, sometimes a delivery service for volatiles. Beyond planets, there have been suggestions from millimeter observatories of cold dust belts around Proxima, which, if confirmed and characterized, would hint at leftover building blocks or ongoing collisions in an outer reservoir. Dust matters to observers because it creates zodiacal light that can swamp faint planetary signals. It matters to planets because it marks a supply line for late water and organics. Now add the star's personality, flares frequent and sometimes intense. A system with multiple planets and dust moving inward meets a wind and radiation field that can charge, erode, and chemically process surfaces and atmospheres differently on each world. For Proxima b specifically, neighbouring bodies can raise or damp tiny eccentricities and obliquity. Even a small residual eccentricity under strong tides can flex the interior and add tidal heat, nudging volcanism and gas release. Over hundreds of millions of years, a modest drizzle of impacts can replenish atmospheres and oceans. A rain of giants can sterilize or strip. The likely truth sits between a low-level background punctuated by rare big hits, modulated by the exact mass and spacing of any siblings we have yet to pin down firmly. For exploration, the architecture shapes where we point next-generation instruments. If an outer cool planet exists, direct imaging at longer wavelengths might catch it first. If dust is heavy, coronagraph designs and observing strategies must cope with a brighter background. For habitability, the take-home is that Proxima b is probably not alone, and siblings plus debris can be either friends or foes depending on timing. A lively asteroid-comet economy early on might have helped a stripped world rebuild. A quiet dust-poor system might have left a survivor dry, but safe. Untangling this neighbourhood story is part of making any confident claim about what B is today. Because Proxima b probably doesn't transit, we can't backlight its air with starlight the way we do for many hot Jupiters. So we lean on three families of techniques. First, keep sharpening radial velocity. Instruments like Espresso and Xpres push down to tens of centimeters per second precision on quiet stars. M-dwarfs are feistier, but long, careful campaigns and machine learning filters that recognize stellar activity patterns can still tease out small signals. RV won't give us air, but it pins mass and hunts for siblings, which sets surface gravity for climate inferences and tells us the system's layout. Second, chase direct imaging from the ground with extreme adaptive optics on the coming generation of extremely large telescopes, ELT, GMT, TMT. Proxima b's angular separation from its star is only a few dozen milliseconds, far too tight for current space telescopes, but a 30 to 40 meter mirror has the raw resolving power to work at those inner angles in the near infrared. Combine a top-tier coronagraph to suppress starlight with high-dispersion spectroscopy to look for the planet's Doppler-shifted spectral lines, sliding back and forth over an orbit, and you get a technique called HDC, high-dispersion coronagraphy. It uses the planet's own spectral fingerprint, blurred reflections of the star plus any atmospheric lines, as a matched filter in a sea of speckle noise. Even a first detection of reflected light would be a milestone. You could estimate albedo, phase variations, maybe even see broad molecular bands in stacked data. Third, plan for future space coronagraphs and star shades. NASA's next flagship concept, the Habitable Worlds Observatory, is being scoped to directly image rocky planets around nearby sun-like stars. Proxima b's tiny separation makes it a worst-case target, but technology marches. Advanced coronagraphs push inner working angles downward toward a few lambda over d. A sufficiently large stable space mirror could, in principle, pick out Proxima b in reflected light at visible wavelengths, though it's right at the edge. Mid-infrared interferometers, constellations that synthesize a giant aperture, could instead look for thermal light from the planet, where the contrast with the star is kinder. Concepts like LIFE, a proposed mid-IR interferometer, speak to that path. Alongside these, watch for photometric and spectroscopic monitoring of Proxima itself, mapping its flares, rotation, and magnetic cycles, because an accurate stellar spectrum and activity model is half of any atmospheric claim. Put these together, and the roadmap becomes patient but clear. Nail the mass and siblings, monitor the star, attempt ELT-class HDC in the 2030s to seek the first reflected photons, design space missions that can work at very small inner angles or in the mid-IR, and when signals appear, stack seasons to see if they change with expected weather and phase. We will not wake up one morning with life detected on a single spectrum. We will accumulate hints, albedo, heat transport, clouds, CO2, H2O, until the picture of sky versus stone comes into focus. Traveling to Proxima Centauri is not like a long airplane flight. It is more like trying to nudge a grain of dust across an ocean using only the heat from a candle. The distances are so large that our first design rule is modesty. Pick one job, usually a flyby, and optimize ruthlessly. The core constraints are speed, energy, mass, shielding, pointing, and time. Speed decides whether a human generation can see results. If you cruise at 0.2 c, 20% of light speed, you cross 4.24 light years in about 21 years of ship time, plus a few years to accelerate and the 4.24-year delay for your pictures to get home. Drop to 0.1 cent and the cruise doubles. At 0.01 cent, you're talking centuries. Energy explodes with speed. Kinetic energy scales with V squared. A 1 kilogram probe at 0.2 c carries about 1.8 times 10 to the 16th joules of kinetic energy, comparable to a large power plant's output over days, so you dare not waste much on turning, braking, or heavy armor. Mass therefore must be tiny if speed is high. That is why the most practical first concept favors gram to tens of grams spacecraft that ride a beamed sail. Pour power in from home while the probe itself remains feather light. Shielding is a dilemma. At 0.2 c, a grain of dust hits like a bullet. Even atoms erode surfaces. The local interstellar cloud is thin, but not empty. The current best trade is a sacrificial Whipple shield up front. Thin layers spaced apart so incoming grains vaporize in the first layer and the plasma cloud expands before it reaches the second, plus a small standoff boom so debris can spread before touching the payload. Some studies add a forward plasma bow, ionized gas pushed by a tiny magnetic field to charge and deflect dust. Pointing matters because communications and cameras must aim with microradian precision after decades of thermal cycles, radiation, and no servicing. The fix is redundancy, several star trackers, gyros, and cameras. Bright beacons at home to help the craft solve its attitude, and very simple testable software. Time is the quiet tyrant. Electronics suffer bit flips from cosmic rays. Coatings outgas. Batteries age. Spacecraft that can hibernate most of the way and wake on timers or starfield triggers have a better chance. Finally, you must choose between accelerate-only flyby, fast arrival, but minutes to hours on target, and accelerate plus brake, slower arrival, but the ability to linger. Braking is brutally expensive in mass and energy. That is why the simplest, soonest path is a fast flyby. Sprint, snap, beam back, and accept that the science window near Proxima b might last hours. That sounds thin, But remember what a fast scout can do. Wide-angle images on approach to map the system. High-speed, high-frame-rate close passes to capture the planet's terminator, cloud patterns, and thermal glow. Spectra of star and planet before, during, and after closest approach. Magnetic and plasma readings of the stellar wind, and geometry tricks like watching the star flicker behind the planet's edge, occultations, to back out air density. The trick is to make 10,000 tiny decisions early: materials, error correction, data compression, camera gain, beam divergence, so that the last hour near the target blossoms instead of blurs. A beamed light sail replaces onboard propellant with light pressure from a phased array laser at home. The sail is a mirror as light as spider silk, perhaps square meters to tens of square meters in area, carrying a postage stamp-size probe weighing grams to tens of grams. When the array fires, photons reflect off the sail and push. Because the sail is so light, thrust per watt is meaningful. The pitch is simple. Build a multi-gigawatt array, accelerate for only a few minutes, and the probe leaves the solar system at 0.2 C or more. The reality requires cleverness. First, the array must keep the beam tight. Diffraction wants to spread light. To keep power on a small sail at millions of kilometers, you need a huge effective aperture and exquisitely synchronized phases so the beam stays pencil thin and rides the sail for the full burn. Second, the sail must survive gigawatts of light without melting or wrinkling. Materials like dielectric metasurfaces, nanoscale patterns that reflect specific wavelengths with low absorption, look promising, as do graphene composites and multilayer films tuned for high reflectivity at the drive wavelength. Third, beam riding stability matters. If the sail yaws or pitches, it can fly off the beam and lose thrust or tumble. Engineers shape sails with passive stability, a slight curvature or center of mass offset, so the light itself recenters the craft. Fourth, the payload must be a full spacecraft in grams, a camera, a spectrometer, a star tracker, a microprocessor hardened by error-correcting memory, a laser downlink for data, a thin film radioisotope or beta-voltaic trickle power source, and possibly a sail as antenna on the way home. Breakthrough Starshots sketched this architecture: a hundreds meter to kilometer scale laser array on Earth or in orbit, thousands of cheap identical sails launched in waves, so a few survive dust hits and unlucky failures, a cruise of approximately 20 years at 0.2 C, and return signals that Earth catches with giant telescopes acting as receivers. Even with perfect optics, the downlink is hard because the probe's transmitter is tiny, and the beam must be aimed across light years while the craft is slewing during flyby. The response is swarm strategy. Send many probes, each tries a different pointing pattern and compression mode, stack partial images using very long baseline receiving arrays at home. Can we break with a sail? In principle, yes, if the same laser that pushed you can be retargeted years later to push backward, or if you route by Alpha Centauri A or B first and use a photogravitational assist, surfing starlight and gravity, to slow and bend toward Proxima. That requires exquisite navigation and longer trip times, but keeps the spacecraft feather light. Another idea is a magnetic sail that unfurls a big superconducting loop. As the craft plows through the thin interstellar plasma or into Proxima's stellar wind, the loop's magnetic field pushes on charged particles and trades kinetic energy for heat, drag braking without propellant. The loop must be huge to matter at 0.2 C, so many studies favor fast flyby now. Captured missions later when arrays and materials grow up. The deeper point is that beamed sails convert ground infrastructure into speed. You pay once to build a laser, then launch thousands of scouts. The first images may be grainy. By the 100th shot, techniques and sails mature and pictures sharpen. That learning curve is how we go from first hello to system survey without ever lighting a chemical engine. If a Gram-class sail is a sprinter, a nuclear ship is a cargo train, slower to start, harder to build, but roomy and capable once it arrives. Concepts like Project Daedalus, 1970s, imagined a fusion-powered probe using pellets of deuterium/helium-3 ignited in rapid bursts, throwing plasma out a magnetic nozzle to reach approximately 0.1 C over a few years of burn. A modern descendant, often called Icarus, explores updated fuels, inertial confinement drivers, and ways to mine or pre-package helium-3. The appeals are control and onboard energy. You can throttle, course correct, run powerful instruments, and possibly brake using a portion of your propellant for a capture burn. The costs are mass and complexity. Fusion engines are not yet flight ready. Fuel is bulky, and waste heat must be carried away by radiators the size of fields. Fission options exist. High-performance fission fragment rockets that let fast fission products stream out directly. More conventional nuclear electric systems where a reactor drives ion engines, or bold nuclear pulsecraft, Project Orion, that eject small nuclear charges behind a pusher plate and ride the blasts. Orion-like ships could, on paper, reach 0.03 to 0.05 C, making Proxima a century-scale trip, slow for news, fast for civilization. They could also carry ton-class payloads, orbiters, landers, atmospheric probes, and Sirius telescopes to map the system from within. Nuclear electric systems are gentler. Duty cycles of years, ion or Hall thrusters sipping propellant, speeds more like 0.01 C unless you carry vast power. All nuclear options must solve shielding, protecting crew or electronics, long-term reliability, and interstellar erosion. At 0.05 cents, dust hits still bite. You need layered shields, perhaps sacrificial ice panels you can replenish from onboard stores. The prize is time at target. A fission electric or fusion probe that breaks into the Proxima system can spend months to years mapping the star's wind, imaging planets at many phases, performing radio occultations to measure atmospheric profiles, and releasing smaller subprobes for close passes. It can loiter near the terminator of Proxima b and watch cloud belts evolve. It can track flare impacts on the planetary magnetosphere. It can triangulate with Earth for stereo imaging. Even a partial break, arriving at say 0.01 C, and then using a mag sail to shed the last bit of speed in Proxima's wind, can stretch the science window from minutes to days, which changes everything about what you can learn. The catch is calendar time. A 0.03 C ship launched in 2100 arrives around 2235. If humanity is patient and stable, that is not out of reach. Most teams therefore imagine a ladder. First, gram-sail flybys to answer air or stone. Next, heavier precursor probes to test braking and comms. Then a decadal flagship that commits to a century cruise with the means to stay. Because such a ship carries power, it can also unfurl a receiver array on arrival to help future tiny flybys dump data by relaying at short range and then beaming home with a big dish or laser, turning the first heavy ship into a beacon and base for the faster trickle of scouts that follow. Acceleration is hard, deceleration is often harder. A Starshot-style probe arrives at approximately 0.2 C. To stop at Proxima, it must dump nearly the same kinetic energy it gained, without a handy laser behind it, unless Earth can point a beam across light years at just the right time and angle. One dreamy option is the photogravitational assist, Aim first for Alpha Centauri A or B, which are bright sun-like stars. Approach on a trajectory and sail orientation that uses starlight pressure plus gravity to break and bend the path, like tacking a sailboat into wind. With precise control and a reflective sail, you can, in principle, slow enough to swing inward toward Proxima, and even capture if you accept longer travel times and lower initial speeds. This trick gets easier at 0.02 to 0.05 C, but stretches cruise to many decades. Another family is magnetic braking. A mag sail, a loop of superconducting wire kilometers across, creates a magnetic bubble. As the craft plows through the thin interstellar plasma or enters Proxima's stellar wind, charged particles are deflected. Momentum exchanges slow the craft. A plasma magnet variant uses driven currents to inflate a larger virtual loop. These can, on paper, shed tens to hundreds of kilometers per second efficiently in a stellar wind. Shedding thousands, what you need from 0.2 C down to bound speeds, is a marathon and calls for large structures and long times. An electric sail, charged tethers kilometers long, pushes on solar or stellar wind protons. It's excellent for inner systems, modest for interstellar braking. Aero capture in a planetary atmosphere is not realistic at relativistic speeds. You must slow first. Gravity assists from planets help once you are in the system, not at entry. Beamed braking, using the home laser years later to push backward on the same reflective sail, is elegant but requires beam access to the craft's aft side and astonishing pointing over light years. A hybrid is staged missions. First send slow, heavy braking infrastructure, a magsail tug, or a beamed power receiver. Then send faster scouts that rendezvous and hand off momentum or draw power to brake. Rendezvous at tens of thousands of kilometers per second is exacting. You would likely aim for slower scouts you can actually catch. There is also proton scoop drag, Bussard ramjet in reverse. Extend fields to gather interstellar hydrogen and expel it, but at local densities, the drag often exceeds thrust unless your fields are enormous. Given all this, the most credible near-term path is simple. Accept flyby first. A fast scout does not stop. It uses burst science at closest approach, a pre-planned sequence of exposures and spectra at millisecond to second scale timing, then spends months after the pass beaming data home with a tight laser link. You stack many probes so chance and dust don't doom the mission. Meanwhile, technology for mag sails, star-to-star photogravity, and beamed braking matures. When a captured mission finally flies, it will do so at lower cruise speeds and with larger structures that unfold and work for years in the Proxima wind. Think of it as building harbours. First you chart the coast with a skiff at speed. Later you tow in pilings and lights. Finally a ship arrives that can anchor and stay through winter. Each rung answers new questions, and together they turn Proxima B from a point of light into a place. A fast light sail scout has one crucial advantage: known geometry. Years before arrival, we can choose an approach that skims the terminator of Proxima B, where a possible atmosphere is most legible, rather than charging straight across the substellar point. The payload must be brutally simple and pre-tested for decades of drift. A wide camera for navigation and context, a narrow imager/spectrograph to stare at the planet's limb, a magnetometer on a boom, plasma and dust counters up front behind a sacrificial shield, a radiometer or filtered detectors to sample thermal glow in near IR bands, and star trackers that double as science eyes in emergencies. The timeline is scripted like a ballet. Weeks out, the wide camera gathers system context, star color, flare statistics, any bright dust that could swamp imaging, maybe even a hint of other planets by reflected light if the craft has a few percent of a year to integrate while coasting in. Hours out, the probe flips to place its Whipple shield forward and locks the narrow spectrograph onto the planet's bright rim. As the planet slides across the star from the probe's perspective, a grazing occultation we designed on purpose, starlight skims through any air. The spectrograph records a stack of transmission spectra, thin fingerprints of CO2, H2O, maybe CH4, or CO if they are present and not masked by clouds. Seconds later, at closest approach, we switch to emission and reflection, limb-resolved images to hunt a bright cloud cap at the substellar point, darker belts toward evening, and the contrast between day and night that betrays heat redistribution. A modest polarimetric mode, just 2 orientations, can reveal how cloud droplets or haze particles scatter because polarized light swings with particle size. The magnetometer reads the stellar wind and any planetary magnetopause crossing. Even a brief kink in the field vector tells us whether the planet pushes the wind back or simply hides in it. Dust counters and plasma analyzers write a diary of grain hits and charged particle densities. Together with the field data, these paint a first portrait of Proxima's space weather, where a planet actually sits. If the approach skims a dark hemisphere, the radiometer may catch a thermal phase gradient, warmer toward dusk, colder toward midnight, that constrains wind strength and night-side temperatures. Everything is compressed, millisecond exposures at closest range, microslews preloaded, a fault-tolerant script that keeps running if any single sensor hiccups. After the pass, the probe keeps the planet in view for as long as possible to record a stellar occultation, watching the star set or rise behind the limb, to back out scale height, a pressure-temperature clue, from the way starlight dims. We do not need perfect weather. Clouds are data too, because their geography and brightness tell us about convection and stability. The last step is triage. The craft condenses raw frames to key thumbnails and feature vectors, applies lossless compression to spectra, flags any transient events, flare scene, magnetopause crossing, and lines up a transmission schedule. One scout's dossier may be thin. A swarm, dozens launched years apart, builds a time series. Same geometry, different space weather moods, richer statistics. With 2 or 3 lucky passes that catch the limb cleanly, the difference between a bare rock and a breathing world becomes testable, even from a probe that weighs less than a songbird. The hardest engineering word in interstellar exploration is link budget, the cold accounting of how many photons leave the probe, how many survive spread and jitter, and how many a telescope at Earth will actually count after 4.24 light-years. A Gram-class scout cannot carry a big transmitter, so we lean on lasercom at a single, clean wavelength, a narrow divergence beam using the sail or a tiny deployable optic as the transmitter's aperture, and photon counting detectors at home. Pointing is merciless. The beam must hit Earth while the craft screams past Proxima b, slewing through pre-programmed pivots as it swaps from science attitude to downlink attitude. The trick is to split the job. During closest approach, the probe spends every joule on science and buffer storage. Hours after the pass, when the geometry settles, it pivots to a steady attitude guided by starfield locks and begins a burst downlink. A beacon on Earth, an uplink laser aimed along the expected arrival path, can help the craft solve its attitude by centroiding on the beacon's speckle pattern. The probe does not need to decode data, only to recognize where home sits and keep its transmit beam glued there. On Earth, we stack receivers, a ring of large telescopes, ELT class and smaller, acting as a photon farm, each with low-noise superconducting nanowire detectors or avalanche photodiodes. Coherent detection, mixing the faint signal with a local laser at the same wavelength, buys more margin at the cost of exquisite stability. Direct detection is simpler but tolerates fewer losses. Either way, we assume the downlink lasts days to weeks as the probe coasts outward and keeps Earth in its narrow transmit cone. Every layer leans on error correction, rateless codes that adapt to changing signal quality, interleaving that smears burst errors from clouds or flare-driven jitter. And ARQ, less strategies, no please repeat messages because the round trip is years, that seed extra parity into the stream so ground can reconstruct missing blocks without asking again. Compression is the second hero. Raw images become wavelet pyramids. The probe keeps sharp features and throws away smooth redundancy. Spectra are lossless but trimmed to useful bands. Magnetometer and plasma data are summarized into high-time resolution snippets around events and coarser elsewhere. A cleverly designed priority ladder lets the probe send the headline products first. Limb spectra, closest approach frames, any occultation curves, so even if the downlink ends early, science survives. Power is the quiet limiter. A thin beta voltaic or trickle radioisotope source can keep a watt-scale laser pulsing for minutes at a time with supercapacitors smoothing bursts, or the sail surface itself can carry PV patches that harvest Proxima's light after the pass, but flares and geometry complicate that plan. The craft therefore cycles: charge, aim, fire. A coded burst, rest, repeat. Back home, we calendar the sky. Receiver arrays track weather, and hand off in chains so the stream rarely hits clouds. Finally, we confess to redundancy. Many probes. Not because we expect failure, but because interstellar space is rude and statistics are kind. 10 downlinks merged yield cleaner spectra, 100 snapshots stack into maps, and 1,000 photons learned the hard way become the design of the next transmitter. The link is not a single shout, it is a whispering choir trained to be understood. Patience is a strategy, not a delay. Long before any sail leaves home, ground and space telescopes will keep turning Proxima b from a rumor into a profile. Radial velocity campaigns continue to shave down noise and star-spot confusion, locking the planet's minimum mass and finding or dismissing siblings that affect long-term climate and impact rates. The next generation extremely large telescopes with extreme adaptive optics and coronagraphs are designed to work at inner angles only a few dozen milliseconds wide, right where Proxima b hides. In the 2030s, first reflected light detections from the ground in the near-infrared are plausible. Not pretty pictures, but the planet's albedo glint and phase changes buried in speckle noise teased out by high-dispersion spectroscopy that rides the planet's Doppler shift as a signature. If we can measure a phase curve, how brightness changes as day and night rotate past us, we get the first hint about heat transport. Big swings imply a bare or thin air rock. Flatter curves imply clouds and air moving heat around. In parallel, stellar monitoring from ultraviolet to infrared maps. Proxima's flare statistics and wind proxies, anchoring any atmospheric claims in real space weather. The 2040s are the hunting ground for mid-IR interferometry concepts from space. Multiple small telescopes acting as one to look for thermal emission from rocky worlds near nearby stars where contrasts are friendlier. Even a coarse thermal detection of Proxima b, hotter day, colder night, or a softened gradient would be a climate breakthrough. By then, the groundwork for a beamed sail array could be in place. Laboratory sails that survive megawatts per square meter. phased array tiles that hold phase over seconds, atmospheric compensation to punch a clean beam up through air, and safety regimes that keep eyes and satellites clear. A realistic path sends precursor sails to the outer solar system first, testing beam riding, laser comm, and shield erosion at high speeds of tens to hundreds of kilometers per second. Not yet relativistic, but enough to learn. The first interstellar flyby wave might then launch late 2040-50s to 2050-50s if the laser array scales, or later if we choose the safer route of space-based arrays that skip air entirely. Cruise at 0.2 C takes roughly 20 years. Add 4+ years for downlink photons to get home. That puts earliest pictures from a fast scout into a 2070s to 2080s window in an optimistic line, or later if we prioritize reliability over speed. Meanwhile, a heavier, slower nuclear electric or fusion precursor, if ever green-lit, is a multi-decade build and a century cruise problem, something a patient civilization can do in parallel once Sail Scouts confirm that the target merits a ship that can stay. The staircase looks like this. 1. Titan mass and siblings with RV. 2. Detect reflected/thermal light and phase behavior from ELTs and interferometers. 3. Sail tech demos in deep space. 4. First interstellar flyby swarm. 5. Optical receiver arrays on Earth. Mature into a permanent interstellar ground segment. 6. Captured mission planning with magsail/photogravity tools. 7. Arrival infrastructure that can serve as a local relay for future scouts. Each step yields value on its own. None waits idly for the rest. It is natural to imagine a window seat on a ship to Proxima, but physics is plain. With today's or near-future tech, humans are heavy, fragile, and hard to keep alive for decades without resupply. A crude interstellar ship needs radiation shielding thick enough to tame cosmic rays and solar storms. At 0.05 C, it also needs dust shields that can absorb or deflect grains, hitting with rifle-to-cannon energy. Life support must be closed loop, air recycled, water recovered, nutrients rebuilt from waste, and systems able to swap parts with onboard manufacturing for years. Power must be steady and ample. Fission is mature, but needs shielding and fuel mass. Fusion would be ideal, but remains unproven in space engines. The ship must shrug off micrometeoroid erosion for millions of kilometers, hold pressures, damp vibrations, and keep psychology healthy in a world with no new air and few surprises. Distances magnify governance risks. Decisions cannot be micromanaged from Earth. Crews or generations must write their own law. That points to two broad human paths, both hard. One is the sprint habitat, reach high fractions of light speed with a huge, powerful engine, arrive in decades, brake, and settle, technically towering and energetically staggering. The other is the world ship, a slow, self-sufficient habitat that takes centuries, with generations living and dying aboard. World ships trade speed for stability. They become places, not vehicles, with agriculture, schools, arts, and politics. Either way, robots scout first. They are lighter, can sleep between tasks, suffer radiation quietly, and can be replaced at scale. They can also prepare. If Proxima b is clement only at a twilight ring, robots can place power relays, dig regolith shelters, deploy inflatable habitats, and start ISRU, in situ resource use, melting ice, cracking water, printing parts, testing soils, and mapping safe tracks. If Proxima b is harsh, robots can still build orbital habitats in the Proxima system using local rock and metals, tapping stellar power with flare-aware grids and storage sized for long, moody eclipses. Humans might then live in O'Neill-style colonies, visiting the planet by telepresence or cautious sorties. Even bold concepts, hibernation, torpor, to lower metabolism, genetic or pharmacological tweaks for radiation tolerance, magnetic shields to deflect charged particles, add complexity but do not break the main constraint. Mass times speed equals energy you must supply and then remove for braking. The humane way forward is to let robots lay roads and verify that a destination can keep people healthy and free. Only then do we argue about ship size and social design. The romance of first footprints is strong. The quiet realism of first data is stronger because it tells us what kind of boots we would need and whether we should step there at all. Suppose decades of scouts and perhaps a captured robotic mission find a Proxima B that breathes, air of some thickness, water in some form, a climate that moves heat. Settlement still means adaptation to a red dwarf sky. Flares are routine. Any surface base would favor low latitudes near the terminator for mild temperatures and build with layered protection, natural berms or regolith for radiation shielding. Double roof designs where the upper sacrificial layer takes UV and particle hits, and storm rooms with extra mass and magnetic coils for the rare violent events. Underwater or underground habitats are attractive. Water is superb shielding, and a shallow sea on the twilight ring offers stable temperatures and steady power from ocean thermal or tidal gradients. On land, greenhouses would be multi-spectrum. Outer panes tuned to pass the most useful near IR for crops under Proxima's red light, while filtering harsh UV. LED grow lighting fills spectral gaps during flares or long clouds at the substellar cap. Because the day sky barely moves on a synchronous world, solar arrays can be fixed toward the star, but the grid must be flare smart. Fast disconnects to protect electronics, storage scaled to ride through storms, and possibly power beaming along the terminator to chase local demand. Wind at the ring, driven by day-night circulation, adds a steady secondary source. Water cycles would be unusual. If nightside glaciers carve into the ring and sublimate on the day side, settlers might site desal plants where night melt meets day heat, closing loops cheaply. Transport follows climate, airships or gliders, surfing the permanent winds along the ring. Rugged crawlers with radiation shelters for nightside excursions, submersibles where seas exist. Agriculture faces a new light, crops bred or engineered for red-shifted photosynthesis, mosses and algae that thrive under low blue and high near IR, and soil microbiomes tuned to local mineralogy. Medicine watches for UV skin damage on careless days and for sleep rhythm shifts in a world without sunrise. Lighting inside habitats would enforce human circadian cues. In orbit, larger populations might prefer rotating habitats with Earth-like gravity, teleoperating factories and mines on airless bodies at safe remove from Proxima's direct tantrums. A magnetotail, if the planet has a field, could host shielded stations. In its absence, large superconducting loops can generate local fields for particle deflection around habitats. Culture adapts too, holidays tied to flares, lights dim, everyone gathers. Work that flows with wind peaks, schools that teach space weather like Earth teaches tides. And ethics walk with us. If Proxima B shows native chemistry or even life, settlement choices narrow to preserve first. In that case, human homes grow in orbit and on dead rocks. The planet remains a park, visited lightly. The point is not conquest, it is belonging without harm in a place whose rules are new. Red light, patient winds, a sun that naps and rages. We met a small, likely rocky world circling the star next door, close enough for telescopes to tease, but far enough that ships must be light and clever. We learned that words like habitable zone are invitations, not promises. That red dwarfs are generous with time, but harsh in youth and moody forever. That a planet can be both extreme and welcoming if air survives and heat circulates. And that the most forgiving geography may be a ring of perpetual evening where winds never tire. We mapped end states from bare rock to ocean world, traced how substellar clouds could shield a dayside, how thin air can still keep a night from freezing, and how gases pile into signatures that can fool or persuade. We sketched how we'll learn more without transits, sharpened wobbles for mass and siblings, ELT class imaging for reflected and thermal hints, high dispersion tricks that ride the planet's own Doppler beat, and one day, direct photons from a craft that weighs less than a sparrow. We faced the hard parts, link budgets across light years, shields that turn dust into harmless vapor clouds, scripts that run flawlessly when no hand can help, and downlinks that make a whisper legible to a patient ring of telescopes at home. We placed the steps on a calendar that stretches longer than a headline and shorter than a civilization. Better spectra from Earth in the next decades. Sail tech that learns in the outer solar system. First flybys that trade mass for speed. And later, captured probes that can stay. We were honest about people. That robots lead because they are light and durable. That human ships are possible when we build places that travel, not only vehicles. And that if a world is alive or fragile, the kindest homes for us may circle above it, not trample it. Proxima Centauri is not a promise of a second Earth. It is a mirror held up to our tools and our patience. If we go slowly and well, we will answer a near question that carries far. Can rocky worlds around the galaxy's most common stars keep air and water long enough to matter? And we will do it by stacking small certainties into a truth large enough to sleep on. Thank you for traveling this quiet road with me. May your room be dim, your thoughts unhurried, and your dreams wide enough to hold a red sun over a calm ring of twilight. Thank you for listening, and good night.